Hi and welcome. Today we're going to talk about polar coordinates, which is section 11.6. This is going to be the topic that we'll be covering today and our last day of class, which will be on Wednesday. Today we're going to talk about what polar coordinates are and have a little bit of an introduction to graphs of graphs using polar coordinates. And then on Wednesday we're going to talk about functions that involve polar coordinates and some of the graphs of those functions. Now, this particular topic is kind of a fun topic, and it's also a topic that you will definitely see in Calc 2 and absolutely 100% in Calc 3. So seeing them now is kind of an introduction that will help you in your future classes, but it really is a big idea in trigonometry. So before we talk about polar coordinates, let me tell you about rectangular coordinates, which is the coordinate system that you are really comfortable with already. So when we have rectangular coordinates, we describe a point P with an x coordinate and a y coordinate, and you already know this. And if you wanted to plot a point like the point x comma y, then you would move a distance of x in the x direction, and then you would move up a distance of y in the y direction, and then you would plot that point, and that would be your point P equals xy. All right, so this is rectangular coordinates, and you've been doing a lot with rectangular coordinates for many, many years. Okay, so let's talk about polar coordinates now. So with polar coordinates, when we have a point P, we describe the point P with an ordered pair where the first coordinate is r and the second coordinate is theta. And the way that we plot this point is we still plot this point in the xy plane. Here's x and here's y. But what we measure is we say, okay, here's this point P, and we measure the distance from the origin out to that point. That is our distance r, and the angle from the positive x-axis up to this line segment, which we call OP, that is our angle of theta. And so we can write this specifically as theta is the angle from the x-axis, meaning the positive x-axis, to the line segment OP. And r is what's called the directed distance from the origin to the point P. And we'll talk about what this word directed means as we look at some examples. For now, think of r as the distance from the origin out to the point P. Now, these two labels are labels that you've seen a lot this semester. You've seen this angle of theta, which is measured from the positive x-axis, and then we swing either in a counterclockwise direction for a positive angle or a clockwise direction for a negative angle. And we had this measurement from the origin out to a point, and that was our r value, which we thought of as our radius or as our hypotenuse. Okay, so we want to get comfortable with plotting points. So we're kind of going back to the very beginning. Like when you first started talking about rectangular coordinates or the Cartesian coordinate plane, when you started doing that, some of the first things you did was plot points. So given the point 3, 2, how do I plot that in the xy plane? I move over 3 and up 2, and I draw the point. So we want to get almost as comfortable with polar coordinates as we would with rectangular coordinates. So let's look at some examples. So our first example, well, in these first several examples, we are going to sketch the point that is given in polar coordinates. All right, so our first example we're going to call A, and this is the point 1, pi over 4. All right, Now, if you are walking down the street and this ordered pair jumps out at you from a dark alley and says, here I am, 1 comma pi over 4, and you're asked to plot this point, it is not at all clear whether this is a polar point, meaning that this first point represents r and the second component represents theta, or if this is a rectangular point where the first component is the x value and the second component is the y value. So you have to know what the context of the problem is in order to know whether this is written down in polar coordinates or in rectangular coordinates. So here we're told these are polar coordinates. Okay, so here's how we might think about drawing this point. Now, when we start, I start by drawing the xy plane, because typically we draw the polar coordinates on the xy plane. Okay? And usually when I start to look at one of these problems, the first thing I do is I look at the angle. And in this case, the angle is pi over 4. Now, I have this handy dandy ruler, and I have some markings on this ruler. I have a distance of 1, a distance of 2, and a distance of 3 on this ruler. So the way I think about this is I take this ruler and, I have a wall over here. I can't quite extend it as far as I want to, but you'll get the idea. So I take this ruler and I swing to an angle of pi over 4. Now pi over 4 is 45 degrees, positive, so counterclockwise. So we swing up to an angle of pi over 4. So on my drawing, I'm going to draw an angle of pi over 4 radians. So here's my drawing, and then what I'm going to do is I'm going to walk along that angle measurement a length of 1. So if I'm working with my ruler and I swing my ruler up here from the origin, I walk out to a distance of 1. So like in this case, 1 foot along the ruler. Here I'm not going to make it quite a true foot because that would be too big. So I move out a distance of 1 along that diagonal line. And here is my point, p equals 1 comma pi over 4. Now, in terms of a sketch, how do I know when I get to a distance of 1? Well, if I'm in the xy plane, typically I would put marks 1, 2, 3, 4, 5 along the x-axis, 1, 2, 3, 4, 5 along the y-axis. When we're talking about polar coordinates, what we want to think about is I want to think about a circle with a radius of 1. And then I can also create a circle with a radius of 2, and then another circle with a radius of 3, so that once I swing up to an angle of pi over 4, then I walk out along, this is very sad, I know. I walk out along this line till I hit a radius of 1. All right, we better check on Ariana. Hold on. Okay, so my assistant now has her paper and she's ready to study with us. So our second example is that we would like to plot the polar point 2 comma negative pi over 4. So when I plot this point by hand, it's helpful for some guidance to create some concentric circles. Concentric means that all the circles are centered at the origin. So I might create a circle with a radius of 1 and a circle with a radius of 2 and continue outward. And this is similar to the idea of when you create the xy plane, you might mark some x values and some y values on the xy plane. Okay, so we want to plot the point 2 negative pi over 4. Now, negative pi over 4, that's my angle, and that's where I want to start. So I point my arm in the positive x direction. My angle is negative, so I'll be swinging in the clockwise direction to an angle of pi over 4, which is 45 degrees. Okay, so I draw an angle of negative pi over 4. And then from there, I measure along this line. This is like our yardstick. I measure a distance of 2. So I walk 1, here's a distance of 1, here's a distance of 2, and so my point is P equals 2 comma negative pi over 4. Okay. Now, Ariana is a little bit upset about this because she says, well, Diane, I really don't like negative angles. In my opinion, when I think about this angle right here, what I think about is swinging counterclockwise. And when we swing counterclockwise, this particular angle is an angle of 7 pi over 4 radians. So it is also okay to draw our point as P equals 2 comma 7 pi over 4, because the angle of negative pi over 4 and the angle of 7 pi over 4 are coterminal. Remember that word? That we learned that one on the first day of class. Okay, so there are multiple ways. Hey. Anyway, there are multiple ways to describe the same polar point, which is a downside of polar points, but kind of cool in the same respect. Okay, so we've plotted the point 2 comma negative pi over 4, which can also be written as 2 comma 7 pi over 4, and multiple other ways as well. Okay, so our final example of plotting a point using polar coordinates is negative 2 comma pi over 6. So I always look at the angle of theta first, and I'll draw my x and y axes. And the thing that was helpful on some of the other problems was to draw these concentric circles. So I have a circle with radius 1, a circle with radius 2, maybe a circle with radius 3, and this is sort of equivalent to maybe using some graph paper. And in your college algebra class, when you were plotting XY points or maybe drawing graphs in your college algebra class, you might have thought to yourself, wow, I'd really like to have some graph paper. And maybe you went out and you bought some of that blue lined paper that has the vertical lines and the horizontal lines. Well, there's a thing that's also called polar graph paper, and I want to show you a picture of that. So here is an example of what might look like polar graph paper. And so what we can see here is I still can see sort of a vertical line and a horizontal line. Those are my x and y axes. And then I have these concentric circles, and each circle represents a circle with a radius of 1, 2, 3, 4, etc. And then I have these nice sort of common angles marked all the way around the circle. Now, there are a few extra angles in here beyond the ones that we typically talk about. For example, usually our first angle here in quadrant 1 is pi over 6 or 30 degrees. And then we have pi over 4 and pi over 3, so 45 and 60. But to keep these guys evenly spaced around the circle, we have marked every pi over 12 radians and all the way around the circle. So this is an example of polar graph paper, and in your remote assignment you will have some of this polar graph paper at your disposal in terms of drawing these pictures. Okay, so let's go back to our hand-drawn picture. Okay, so we have these 3 concentric circles. Looking at them a little bit more, or from a little farther away, they're not perfectly drawn, but that's okay. All right, so we want to draw this point, and as I've done before, I look at the angle of theta first, which in this case is pi over 6, so I think of that, and pi over 6 radians is 30 degrees. So I can draw my angle of 30 degrees. Here it is. And so if I'm thinking about this in terms of my antenna or my yardstick, I start on the positive x-axis, I swing up counterclockwise to an angle of pi over 6 radians, and then I look at the r value. And so our r value in this case is negative 2. So if this had been a positive 2 value, what we would have done is walked out along this antenna that we've created 1, 2 units and marked our point. Because this value is negative, when we have a negative r value, what that means is the direction that our antenna is pointing is the positive r value, and negative means that we want to point in the opposite direction of our angle, which means that I'm going to take this line and extend it in the opposite direction. All right, so instead of pointing in this pi over 6 direction, I'm going to reverse directions and walk a distance of 2 in the opposite direction. So here we get to our circle of radius 1, here we're at our circle of radius 2, so this is where our point will be. So our point P equals -2 comma pi over 6 is this guy right here. Okay, now I mentioned on the other examples that there are multiple ways to describe this same point, and so we can also describe our point P in the following way. If I think about, instead of having this angle of pi over 6, if I instead swing this angle from our positive x-axis, swing all the way around to that back side of the angle, well, this little piece here is the same angle as over here, so that little reference angle is pi over 6. And so if I swing from the beginning all the way around to this mark that I have here, well, let's see, I have pi to get to 180 plus an additional pi over 6. So this full angle is an angle of 7 pi over 6. And you should double check that and make sure that you can convince yourself that this angle from the positive x-axis swinging pi over 6 past 180, that's going to be 7 pi over 6. Okay, so if we use as our theta value 7 pi over 6, then we're taking our antenna and we're swinging around until we're pointing, now our positive r direction is pointing down and to the left. And so now we walk 1, 2 units, and that's a positive r value. So our point would be +2 comma 7 pi over 6. Okay? That's a second way to describe this point. Another way to describe this point is we could start in the positive x direction and swing in a clockwise direction. And so if I swing in a clockwise direction until I get to this antenna pointing off to the down and to the left, well, this angle, you should convince yourself, is an angle of -5 pi over 6. So we could describe our point as a theta value of 5 pi over 6, and when we swing in that direction, the positive r is the direction that we're pointing, so we would have a +2 as our value. So back at the beginning, when I said that r is a directed measurement, the directed part comes from whether this r value is positive or negative. If the r value is positive, you look at your angle, you swing your arm to whatever that angle is, and then you follow towards your fingers is the positive r direction, and opposite of the direction of your fingers is the negative r direction. Okay, so now we've seen 3 examples of plotting polar points. And now that we have 2 coordinate systems, what we would like to do is to be able to convert between rectangular coordinates to polar coordinates and from polar coordinates back to rectangular coordinates. So that's the next thing we want to talk about, is converting between rectangular, which are sometimes called Cartesian coordinates, and polar coordinates. Okay, so here is a picture of a generic polar point. Here's our point P, and P is measured with r and theta. And so the way that I can write that down is our r value goes from the origin out to the point P, so that is our distance of r, and theta is measured from the positive x-axis to that line segment from the origin out to P. Okay. On the other hand, if I'm talking about rectangular coordinates, then to describe this point, what I do is I create a horizontal side which is my x side, and I create this vertical side, which is the y side. So our point P can be written in polar coordinates with r and theta, or we can describe our point P with x and then y coordinates, which are rectangular or Cartesian coordinates. Okay, so what we want to talk about is relating the r theta version of our point to the xy version of our point. And the way that we come up with some conversion formulas is think about relationships between the x and the y and the r and the theta. And so some things that I might notice about this are that this triangle has all of the important pieces that we've been talking about most of this semester. We have an angle, an x, and a y, and an r. And so these look an awful lot like the labels we have for a lot of our trig functions. For example, if I write down cosine of this angle theta, cosine is adjacent over hypotenuse, or x over r. And if I multiply both sides by r, then what I get is that x is equal to r times cosine of theta. So I multiplied both sides by r, the r is canceled on the right, and I get x equals r cosine theta. I can do the same thing with sine of theta. Sine of theta is y over r. And if I solve this equation for y, I have y equals r times the sine of theta. So these two formulas, x equals r cosine theta, y equals r sine theta, are going to be two of our conversion formulas. The third conversion formula is the relationship between the sides of this right triangle, and that's the Pythagorean theorem, which says that x squared plus y squared equals r squared. So these three boxed formulas are our conversion formulas to convert from polar to rectangular, or from rectangular back to polar. Okay, let's look at some examples. All right, so we would like to convert from polar coordinates to rectangular coordinates. And so our point that we're given is P equals 4, negative 2 pi over 3. Now, if I wanted to, I might draw a little picture of this, and I might say, okay, where does this point live? And I would start by creating a little polar graph with some concentric circles. And I would measure an angle of negative 2 pi over 3, so that's a clockwise measurement of, so pi over 3 is 60, twice that is 120, so 120 degrees in the clockwise direction. And then I would walk a distance of 4 units along that antenna. So 1, 2, 3, 4. So here is our point P that we are interested in. And right now that point has been written in polar coordinates. And we'd like to figure out what the rectangular coordinates are, the xy coordinates. In other words, how far do we need to walk to the left and down to get to that same point? All right, well, what's kind of cool about this is that these formulas right over here, x equals r cosine theta, y equals r sine theta, those are going to give us our x and our y coordinates directly. So let's start with x equals r times cosine of theta. So let's see, we're trying to figure out the x coordinate. Our r value is 4. Our theta is negative 2 pi over 3. So we have 4 times the cosine of negative 2 pi over 3. Now, in order to evaluate this expression, and come up with my final answer. You could type this into your calculator, but that's not the intention. The intention is to come up with an exact value, which we'll do by hand. Okay, so cosine of negative 2 pi over 3. Let's see, negative 2 pi over 3 is the same thing as negative 120 degrees. So if I draw that, I have this guy down here. My goal is to evaluate cosine of negative 2 pi over 3. So if I have that value memorized, great. If not, I might try and calculate it by hand. And so by calculating it by hand, I first draw my angle, and then I create my reference triangle. And looking at this angle, an angle of negative 2 pi over 3 gives me a reference angle of pi over 3, or 60 degrees. And now I know what my sides are because I have a 30-60 right triangle, so my x side is a 1. My side opposite 60 degrees is square root of 3. And my hypotenuse is 2. So we have r equals 2. I want to think carefully about the signs, SIGNs. We're in quadrant 3, so the x value will be negative, and the y value will also be negative. Okay, so now I have my three sides, and I can talk about the cosine of negative 2 pi over 3 is going to be x over r, which will be negative 1 over 2. So our x value, by the way, this x and r is strictly for this little side scratch work on this bar napkin that I'm doing over here that I'm going to crumple up and throw away. But I'm using these letters in terms of this sort of reference triangle that I have here. Okay, so we have cosine of negative 2 pi over 3 is negative 1/2. So x, our x that we care about is 4 times cosine of negative 2 pi over 3, which is negative 1/2. 4 times negative 1/2 will be negative 2. So there's our x value. We're going to need that. And our y coordinate, y is r times sine of theta. So for us, our r value on our problem is 4, and our angle is negative 2 pi over 3. So now I need to know the sine of negative 2 pi over 3, and I might have the sine of negative 2 pi over 3 memorized. If I don't, I have a picture of an angle of negative 2 pi over 3, and the sine will be y over r, which is, so this sine of negative 2 pi over 3 will be negative root 3 over 2. So our y coordinate will be 4 times negative root 3 over 2. And when I clean this up, I can think about this as 4 over 1. I can cancel the 2 on the bottom with one of the 2's on the top, and I'm left with negative 2 times the square root of 3. So this is my y value. And now that I have the x and the y, our point, which here is written in polar coordinates, can also be written as x equals negative 2, y equals negative 2 times the square root of 3, and these are rectangular coordinates. So this is our final answer of converting from polar coordinates to rectangular coordinates. Negative 2 in the x direction, negative 2 times the square root of 3 in the y direction. All right, in this example, we are going to convert from rectangular coordinates to polar coordinates. So here we're given a point which is given in rectangular coordinates. So the negative 3 root 3 is our x coordinate, and the 3 is our y coordinate. So in order to convert this into polar coordinates, in other words, into r comma theta coordinates, maybe the first thing that I might do here is to draw a picture of this point. And we're talking about rectangular coordinates, so we've got an x coordinate of negative 3 times the square root of 3. I don't exactly know what that number is, but it's a negative number, so somewhere in the negative x-axis, so negative 3 times the square root of 3, and our y value is positive 3. So here's that up here. So we move negative 3 times the square root of 3 in the x direction, 3 in the y direction, and here is our point p equals negative 3 root 3 comma 3. Okay, so there's that point, and we would like to describe that point using polar coordinates. So to use polar coordinates, I'm going to need two pieces of information. I'm going to need the distance from the origin out to that point, that's our r value, and I'm going to need our angle of theta, and theta is always measured from the positive x-axis, and we actually get a choice. We can choose to swing in a counterclockwise direction, in which case we'll have a positive angle, or we can choose to swing in a clockwise direction, where we would get a negative angle. I'm choosing the counterclockwise direction because just positive angles are easier, but I would encourage you to think about this in terms of the clockwise direction if you so choose. Okay, so here's our angle of theta, and we want to find a value for r and a value for theta. Okay, now maybe I'll write this guy down here on this side. So now that I have this drawing, I can also put a few more marks on here. This y side is a length of 3. This x side is our negative 3 times the square root of 3. Okay. Now, if I kind of step back and stare at this, I might kind of notice there's something going on with these numbers, and I might say, ooh, that kind of looks like a big version of one of our special triangles, and you might recognize what that reference angle is in there. If that's the case, you can go ahead and write it down. If not, then here's how I would proceed. So I would look at this and say, okay, I need to find a value for r. I also want to find a value for theta. I'm going to start by finding a value for r. And the conversion that I'm going to use is the Pythagorean theorem, which says that x squared plus y squared equals r squared. Okay, so I have my x, which is negative 3 times the square root of 3, quantity squared, plus I have my y, which is 3. That value will be squared, and all of that will be equal to r squared. So when I square negative 3 times the square root of 3, the negative will cancel, so that will become positive. The 3, when I square that, I have 9. Square root of 3 squared is 3. So I have 9 times 3, which is 27. 3 squared is 9. So I have 27 plus 9 is 36 equals r squared. I take the square root of both sides. Our r value that we're going to use, we're going to be pointing toward this point, so that r value is going to be positive, so I'm going to choose r to be 6. Cool, so I now have half of the information I need. I have r equals 6. Okay, now that I have the r value, I want to find the theta value. And I have a couple of choices. I have two conversions. I have that x is equal to r cosine theta, and I have y equals r sine theta. And it doesn't matter which of these two that I choose, but I want to pick one of them, fill in the information I have, and solve for theta. So maybe I'll go with this first one, x equals r cosine of theta. Again, you can choose x or y equals r sine theta and work with that one as well. But x equals r cosine theta, I know that my x value is negative 3 times the square root of 3. My r value is 6, and then we have cosine of theta. And our job is to solve this equation for theta. And so you might say, hey, we've talked about this. We've talked about solving equations where we have trig functions, and that's exactly what we're going to do here. So we're going to take this equation, negative 3 times the square root of 3 equals 6 times cosine of theta, and we're going to solve this equation for theta. So we have negative 3 times the square root of 3 equals 6 times cosine theta. To solve an equation involving a trig function, I see that this trig function is not raised to a power, so my strategy is to get cosine of theta by itself. So I'll divide both sides by 6. And on the right side, the 6's cancel. And on the left side, I can simplify things a little bit. I can cancel the 3 in the top, and that will leave me with negative square root of 3 over 2. Okay, so my job is now to figure out for what angles of theta is cosine of theta equal to negative root 3 over 2. And so you might remember when we talked about solving equations with trig values in them, that what we want to think about is, all right, this ratio is negative, so where is the cosine function negative? And cosine of theta is negative in the quadrants where x is negative. So in quadrants 2 and quadrant 3. All right, so if I was solving this equation, then I would have an angle in quadrant 2 and an angle in quadrant 3. Now, in our context, we know that we're looking for an angle in quadrant 2. So if I was just kind of hanging out solving this equation just out of the blue nowhere, hanging out on the street, then I would have 2 possible angles that would work. In the context of what we're doing, we're looking for the angle that's in quadrant 2, and I know that because I drew a picture of my point already. Okay, so we are looking for this angle, the one that'll be in quadrant 2. So I'll draw my reference triangle. And we have our x value is x equals negative square root of 3, and our r value is 2. And as soon as I see those two sides, I recognize this is one of our special triangles. The third side is 1, and our reference angle will be 30 degrees, or pi over 6. And if I know that this reference angle is pi over 6, then what I need to think about is, what is this angle that starts on the positive x-axis and swings over to our terminal side? The reference angle is 30 degrees, so our angle here is 150 degrees, which if I turn that into radians, that's 5 30-degree measurements, so this becomes 5 pi over 6. I can think about coming up with this angle from the positive x-axis over to our terminal side in a lot of different ways. I can think about blocks of how many blocks of pi over 6 do I need? I need 5 of them. I can convert into degrees and then think about, okay, what is 150 degrees in terms of radians? Convert back into radians. However I want to calculate that value, my goal is to come up with this angle of theta that starts on the positive x-axis and ends on this terminal side. So in solving this equation, if I were solving this equation, straight up solving the equation with no context whatsoever, I would have both this angle of 5 pi over 6, and I would also have this angle down here, which would be 7 pi over 6, but I don't care about that angle because we only care about the picture in quadrant 2. So our angle will be theta equals 5 pi over 6. Okay, so now we have our theta value, we have our r value of 6, and so our point that we originally drew with an x value of negative 3 root 3 and a y value of 3, we can now describe that point in polar coordinates with an r value of 6 and a theta value of 5 pi over 6. So this is r and theta. And we have now converted our rectangular point of negative 3 root 3 comma 3 into polar coordinates. All right, so we've done one example of converting from rectangular to polar, one from polar back to rectangular. You're going to get an opportunity to practice more with these both in the remote assignment and also in the practice problems. So there's a bunch of practice problems on these, and the answers for those are in the textbook. So practice some of those and then work on that remote assignment.